Hello, everyone. So I'd like to tell you a story, and it starts with the news back in April that came from scientists at Harvard and Stanford of the first experimental confirmation of the theory of cosmic inflation. And the slide just advanced on me, and there's no audio. All right. Okay. Right, so what's exciting about this announcement, actually, one of the things that was really exciting about this announcement was the video that I'm about to show you of one of the researchers showing up at the door of the theoretical physicist, Andre Linde, to give him the news. And I want you to see his reaction.
Today, I'm going to deliver a news to Professor Andre Linde, who is the founding father of inflation. So inflation is the theory about the bang of Big Bang. It explains why we have all this stuff in the universe. So today I'm going to tell him our experiment, BICEP 2, based at South Pole, has found the smoking gun evidence of inflation. He has no idea that I'm coming.
Oh, wow.
So I have a surprise for you.
Wow.
It's 5 sigma at 0.2.
Discovery.
Yes.
What? Just a second. Can you repeat it?
5 sigma, as clear as day, R of 0.2.
Can you repeat it again?
R 0.2 plus minus
Point.
Okay, all right, so what's amazing about this video, right, is first off, like, his wife, who is also a respected particle physicist, she gets it first. He's like, what? And she picks up on it immediately, and he still doesn't believe it. And then, why are these slides advancing? At first, he doesn't get it, and then when he kind of absorbs the news, he sort of leans up against the doorway like he's about to faint. And the point of this talk anyway is I want to tell you why you should probably faint too. So I'm going to rewind to the 17th century, right? And I want to tell you about Galileo, and you probably already know about Galileo, but back in his time, people thought that the Earth was the center of the universe, and the sun and the moon and all of the stars revolved around it. But Galileo did something new. He pointed a telescope at the planet Venus, and he discovered something strange. He discovered that we only ever see Venus in phases and never in full light like the other planets. And he reasoned, quite correctly, that this is because Venus is closer to the sun than we are. And so when it's in full light, it's behind the sun and we never see it. And that it revolves around the sun just as we do and just as the other planets do. And then he looked at Jupiter, and in looking at Jupiter, he noticed a line of moons moving back and forth, and he turned this 90 degrees in his head and realized that these moons were revolving around the planet Jupiter rather than around the sun or around the Earth. And in doing so, he turned our concept of the universe on its head. And now today we know, of course, that the Earth is at the center of the universe, and we've discovered the distances through careful measurement to the sun and to the other planets. But discovering the scope of the true scale of our universe was very difficult, because the stars are so immensely further away that it's hard to know exactly how far away they are. So in the 19th century, an astronomer named Friedrich Bessel used a method called parallax to identify the distance to a star called 61 Cygni. Now, parallax is something that we experience every day. If you open one eye, close the other one, and then close the first eye and open the other one, you'll see an object move in your field of vision. And the reason for this, of course, is that your eyes form the baseline of a triangle, and this gives us depth perception. This is called parallax. And essentially what he did was use the Earth's orbit, and took 2 observations 6 months apart, to use the Earth's orbit as a very long baseline. One eye open, one eye closed, and then the other, in order to determine the distance of 61 Cygni. And he found that it was over 65 trillion miles away, which is really incredible if you think about it. It's 11 light years, and no one believed it. It's incredible to believe, right? But we gradually discovered that most stars are even further away, and by the start of the 20th century, it was believed that we live near the center of a Milky Way galaxy, which is about, maybe 30,000, maybe 100,000 light years wide, and that was the whole universe. And around this time, an astronomer named Vesto Slipher was engaged in examining this strange phenomena called spiral nebulae. And the thing that he found about spiral nebulae, he looked at their spectroscopic output, their light spectra, and he noticed that these spiral nebulae, were they clouds of gas, collections of stars? No one knew. He knew that they looked just like ordinary stars, except that their light spectrum was shifted off to the red. And he correctly identified this as a form of Doppler shift. And we experience Doppler shift every day on a daily basis as an ambulance goes by, and the sound of the ambulance siren gets deeper as the light waves stretch out in its wake. And light sources do the same thing. Light sources become redder as they travel away from us as the light waves stretch out. Now, the thing is that Slipher found that the Doppler shift of these spiral nebulae were so great that they ought to have flown all the way out of the Milky Way galaxy all at once. And this was plainly impossible because the Milky Way galaxy was the entire universe, and so no one knew what to make of it. In the 1920s, a researcher at Harvard named Henrietta Swan Leavitt was studying these stars known as Cepheid variables. And Cepheid variable stars have the property that they pulsate in brightness every few days. And in studying countless photographic plates of the Magellanic Clouds, Leavitt discovered that the brighter a star is, the slower its pulsation is. Right? And since we know the absolute brightness of those stars, if we look at how faint they appear to us, we can estimate the distance to them. Right? So now we can measure things that are even further away than we were able to previously. And so Cepheid variable stars became a kind of a standard candle that we could use to measure farther distances out in the universe. And so this gave Milton Humason and Edwin Hubble the ability to look at variable stars in the Andromeda Galaxy. And they found that they were so faint that that meant that the Andromeda, well, it was then called the Great Spiral Nebula in Andromeda, and it turned out to be over 1 million light years away, meaning that it couldn't be in the Milky Way galaxy. It had to be a separate galaxy on its own. And all of the galaxies are separate galaxies, and our universe became immensely bigger all of a sudden. Moreover, Humason and Hubble found that the redshifts that Slipher found were real, and that these galaxies really all were traveling away from us at an incredible clip. Now, how is this possible? Right? This is very strange. Well, a Belgian physicist named Georges Lemaitre, around the same time, had been studying the general theory of relativity, and he found a very peculiar interpretation of these equations, which said that space itself could expand like the surface of a balloon. Right? Now, even Einstein thought this idea was completely insane, which it is, but we have to accept the evidence, right? Like, either these galaxies hate us and they're all fleeing from us, or they're all receding away from each other too. So we have reason to believe that space itself, the space between the galaxies, is expanding at a rate that we can measure by looking at the redshifts of the galaxies, these same redshifts that Slipher examined. And if we look at them, we discover that the universe probably started 13.8 billion years ago in an event that we today call the Big Bang. Right? One of the predictions of Big Bang theory is that the early universe would have been the matter of the early universe would have been too dense for light to escape, and only later, as it thinned and cooled, would light escape out into the universe. And the theory tells us that we should see this today. These light waves would be stretched out into microwaves, and we would see a kind of a cosmic microwave background of noise left over from this time after the Big Bang. And in fact, in the 1960s, researchers at Bell Labs found this pervasive microwave hiss at exactly the frequency predicted by the Big Bang theory, which is really incredible. So there's still some questions that are not answered by Big Bang theory. For example, the universe doesn't seem to have been around long enough for us to be able, for all of the stuff that we see to be spread out so evenly. So the theory doesn't tell us why the universe is so homogeneous. We see the same number of galaxies in every direction. We don't know why. Now, this is a little bit weird. But space appears to be Euclidean, right? Now, it's weird to think of what flatness means in a three-dimensional context, but in this case, you can think of it as meaning that parallel lines always stay parallel and they never converge in the distance. And if space was curved, then parallel lines could converge or diverge in the distance. They don't, right? And we don't know why, but if they did, the galaxies would have never had time to form, or the universe would have crunched back in on itself. Big Bang theory doesn't tell us why this didn't happen, why the universe appears to be totally flat. So in the 1980s, two researchers, Alan Guth and Andre Linde, you remember Linde? This is talk about Andre Linde. They came up with a theory called inflation. And inflation tells us that in the very first trillionth of a billionth of a second, our universe would have expanded by over 20 orders of magnitude or more, from like the size of a grapefruit all the way to the size of the Milky Way galaxy. And this would have two effects. One, it would tend to smooth out any curvature in space and give space the flatness that we see. And would also evenly spread out all of the matter that we see, so that it would create this sort of homogeneous universe that we see today. So the question is, how do we test a theory about something that happened billions of years ago in less than the blink of an eye, before light was even visible? Now, we know that gravity can bend light, right? General relativity tells us this. And inflation theory posits that the very first moment of inflation would send these gravity waves throughout the early universe, like ripples in a pond if you were to throw, the universe in it. Now, we can't actually see these gravity waves directly, but gravity waves, it's known that gravity waves will impart a kind of a curl to light that passes through them. And this phenomenon is known as B-mode polarization. And if we could see we could find B-mode polarization then in the cosmic microwave background, then this might be evidence that inflation actually happened. And so scientists at Stanford and Harvard have built a number of very sensitive microwave observatories at the South Pole to look for B-mode polarization in the cosmic microwave background. And just this April, the announcement that you saw, right, the news that you saw, was that they had found it, right, which is really incredible. I mean, this is actually, I mean, if you think about it, they may have found evidence for cosmic inflation. So I'm going to show you the rest of the video now.
We don't expect anybody. Renata tells it's probably some kind of delivery. Did you order anything? Yeah, I ordered 30 years ago. Finally, it arrived.
Cheers, cheers.
Congratulations.
Oh my God, I'm going to break something.
It's really hard.
They all there. They all three
there.
different experiments.
Yes.
If this is true, this is a moment of understanding of nature of such a magnitude that it just overwhelms. And let's see, let's just hope that it's not a trick. I always live with this feeling, what if I'm tricked? What if I believe into this just because it is beautiful? What if, yes. So this is really helpful to have events like that. It's really, really helpful. Thank you so much for doing it for us.
What you're seeing here is a theoretical physicist, right? I mean, getting news for the first time that his theory, the theory that he's worked on for over 30 years, might actually be correct. And this is amazing, right? And moreover, this result opens up all kinds of possibilities for future exploration. For example, the eventual reconciliation of quantum theory with the theory of relativity, which I don't have time to tell you about. That's the subject of my next talk, I promise. Okay, there's three things I want you to take away from this. One is, note Linda's skepticism at the end, right? Even after having worked on this for 30 years, his commitment to scientific principles is so strong that he refuses to believe for sure that his theory is correct until the evidence is confirmed over and over again, and more experiments are on the way. The other thing that I want you to take note of is his joy at the scope and the immensity of our universe. And I want you to appreciate that. I want you to really feel that, because we live in this universe that is immense in size and complexity, and we're a part of it. And then finally, I want you to appreciate that we, tiny human beings on our little world, may have been able to stare off into the vast reaches of time and space to glimpse the very first moment in time itself. I'm Schuyler Erle. I'm with Idibon, idibon.com. Check us out. Thank you very much.